Perfect. We're starting the webinar. So we're just going to go ahead and wait for the live streams to kick in, and then we'll get ready to start the show, everybody. Just realized I muted myself. Welcome aboard, everybody. We're currently working on getting the live streams all set up. So we have some people joining us on the Zoom. We're also going to be on LinkedIn as well as on YouTube. So give us a couple seconds to get set up. Just in case you're wondering who we are, this is a tech talk, an MLflow tech talk on quick to production with the best of Spark and TensorFlow. So give us a couple more minutes, and we will be ready to start the show. Excellent. We are live on LinkedIn. Thank you. And we're currently just trying to get access to the one on YouTube. Sorry, give me one more second to verify, and then we'll be good to go. Oh, and meanwhile, as you're chiming in, why don't you tell us where are you from, where you're based out of? My name is Denny Lee, and I'm based in the Emerald City, i.e. Seattle, Washington. How about yourself, Rodney?
Yes, hi. My name is Ronnie. I'm a data scientist manager. I'm here in Boston. So yeah.
Perfect. Well, excellent. And so for the rest of you guys and gals, for that matter, please chime in the comments section in LinkedIn, or in the Q&A section for Zoom, or the Q&A section for YouTube. But without further ado, we are up and running. Thanks very much to the Lix Foundation for getting us all set up and running. So this is awesome. So just as a quick start for the show again, this is the Tech Talk, quick to production with the best of Spark and TensorFlow, which is going to obviously feature MLflow. That's why we get the big banner there on the right side as well. I want to go ahead, and the two main people, well, actually the key person, the real person who you're here to listen to is Ronnie. I'll let him introduce himself. I'll be here in the background answering some questions and just helping out in general. One little tidbit before we switch over to Ronnie. If you are interested in listening to more about what Ronnie's going to talk about and many other data professionals, please come to the Data and AI Summit. The link is up there. That's just a short link that you don't actually have to be using Delta Lake. I just happened to use the Delta Lake link, so my apologies for that one. But so definitely register and use the code DAISCOM25. You will get 25% off of training and 25% off the ticket. It is both virtual and on-site, so the tickets are really for the on-site ones. So that's where the DAISCOM25 will help you. Otherwise than that, you can always just join us virtually too, because there are plenty of people who are going to be joining that way as well. So without further ado, I'm going to stop sharing my screen and let Ronnie go ahead and take over. So Ronnie, take it away.
So hey guys, as I said, my name is Ronnie Matthew. I'm a data science manager here at Rogels Group. So if you guys don't know about Rogels Group, we are a fashion e-commerce company. So we have two websites through lala.com and gilt.com. And like our team mainly works on recommendation systems. We work on the forecasting, computer vision, and the whole 9 yards of ML. As we start to the slides, we'll also quickly show what kind of work we do. So yeah, let's start with the slides. I have a few slides here, but feel free to ask questions in social media or like even the Zoom chats. And yeah, I'll try my best to answer all of the questions. So yes, this topic is basically something we learned as we wanted to move towards building a next set of our next generation of our ML products. So we wanted to dive into like deep learning. So deep learning, when people hear deep learning, it also comes with a lot of complicated MLOps code, like if you want to set up Kubeflow or like SageMaker stuff. So this is basically how can, if your existing pipeline is using Spark, this is somehow like we can quickly integrate TensorFlow into the existing pipeline, and then you can do quick iterations and like quick testing, and like test something out before we build it like completely, right? So that's the whole talk about. So what we'll cover in this talk is basically using the best of both of these worlds. We'll talk about what is nice about Spark, what is nice about TensorFlow, and then we'll talk about how we can combine those things. So we'll cover some of the recent advancements in TensorFlow 2 and some of the extension libraries that TensorFlow has for integrating like seamlessly with Spark. So this talk will also cover like how we can do quick distributed deep learning, and then how we use MLflow model registry as our single source of truth for all of our models. And then this also lets you unlock like real-time inference. So basically, if you want to do something like or in-session recommendation, this kind of enables you to like move forward towards that path. So who is this talk for? This talk is mainly for a small or medium full stack data science team who doesn't have like a dedicated team to focus on infrastructure and a lot of the MLOps side, right? So this is for those guys who are primarily working on Spark or TensorFlow-based pipelines. Let's you skip the additional complexities of MLOps code and also like gives the flexibility. So for example, you start with this approach, which is less MLOps, but if you feel like at some point now my whole product is like awesome and I want to just go to production and I want to like get a very reliable, very solid MLOps thing, you have the flexibility to do that. This approach is modular enough to let you MLOpsify like the certain stage of ML, right? So yeah, and then it also lets you move from production to prototype to production like pretty quickly, and enables like rapid prototyping and experimentations. Especially with deep learning models, this is very important because you might end up building a model for a whole year, and once you test it, if this is not performing as you expected, you'll have to go back to the drawing board, right? So the capability to test like a model quickly is very important, especially when you're working with these models. When I say test, it's more like A/B testing or bandit testing, where you're actually putting your recommendation in front of members and you get feedback from them directly. So why do we need like deep learning, right? Like you have normal like deep learning, you have TensorFlow, you have PyTorch, you have a whole set of other frameworks that lets you do deep learning, but why distributed, right? So first thing is when we do distributed, it's also building a model on like a cluster, right? So now you have the ability to like feed in a lot of input features. This also lets you capture more complex features and interactions, right? So especially deep learning models like have a lot of layers which can capture like those features. And especially in recommendation systems, you're working with like clickstream data, right? So this is basically this member viewed these products, or this member purchased these products, or this member added these products, right? So that data can be very huge because it's like every single click on our website, right? So it gets very difficult to train these huge data sets on a single machine. So it's very important to like to distribute it, and so we can get training done much quickly. And it's also not easy for us to subsample our recommendation, the data set, so that, because it's not a full representation, right? Especially when you look at clickstream data, it can include seasonal patterns. It can include like, is it a weekday or a weekend, right? So you have a lot of things that might not be captured if you look at a very small sample of that data. Then finally, like you would also want to train on multiple nodes and also train on multiple nodes with multiple GPUs or TPUs or CPUs, right? So this kind of gives you the opportunity to do all that. So what does this unlock for us, right? So this is basically some techniques, solutions that was unlocked for us. Like basically we can now do deep learning and personalization models and recommendation systems using deep learning. We can now use cutting edge language models, like which is not BERT, but anything that's like latest, like it can be BERT, Elmo, or whatever is coming down the pipeline. You can use those models now in your Spark pipelines, right? You can use these specific named entity models to do product tagging for catalog management and build visual models using autoencoders and CNN and add everything to your Spark pipeline. Finally, you can also do online recommendations, such as like session based or like you can give recommendations to members right when they're on your site, so you don't miss the opportunity to like entice a member with products with your best assortment, right? You can also plug in reinforcement learning if you need into that pipeline. So yeah, the opportunity is like endless. So basically the world is our oyster and you can build whatever solution you want or you were thinking of with deep learning. So yeah, before I go to about us, Danny, do we have anything right now? Any questions?
No, so far so good. Keep on rocking right now.
Cool. So who we are Rogil Group, as I mentioned, we're a fashion technology company based in Boston. We have more than 50 million members who loves our getting exclusive access to private sales. And we have like most of the coveted brands. And our inventory is also changing every day because we have flash sales. So every day you will see like a new set of products on our website. So these are screenshots of two of our websites. One is rulala.com and the other one is scale.com. Feel free to register and get subscribed to sales if you're interested. But our data science team is pretty small. We are like a close-knit group of data scientists, and we work on a variety of projects, including NLP, computer vision, forecasting, and recommenders. We use machine learning to personalize most of our site. So on the site, like you can see some places where we use like machine learning. The first is like sorting our homepage. And then we also use product recommendations in a lot of different places on our site. So previously, until last year, this is how our machine learning stack looked like. We mainly use Spark-based pipelines. So we have data flowing in from the data warehouse. We have S3 buckets. We have like Kinesis streams and stuff, and we do data engineering mostly on Spark, and sometimes on our data warehouse. And then we build most of our models on Spark, but we also use like scikit-learn. We use XGBoost. For forecasting, we use Profit library, and then we use MLflow for our model management. And then we use batch inference, like we have batch inference pipelines in Spark and also in AWS for if it's something very container-based, you can run it on AWS, but if it's like using Spark, we use it on Spark pipelines. Then we have data stores where we put our data to. We use like push data back to our warehouse, push data back to DynamoDB, push data back to S3, sometimes to Elasticsearch. So that's basically our stack that was existing until last year. So we had a need for developing like a next generation of our models, right? We can only do so much with the traditional machine learning. So we wanted to add like new capabilities to our models. So you can add in more features like more signals that's going to help improve our recommendation. So anything next generation right now is deep learning. So we have experimented with like more TensorFlow from like TensorFlow 1 and the first version of Keras and everything. So we were always been inclined towards TensorFlow. I'll also go into reasons why I really like TensorFlow, and then so that's basically what we wanted. So we wanted to expand beyond the Spark machine learning library and leverage state-of-the-art deep learning technologies. So we also wanted the data scientists and ML engineers to actually focus more on research and building actual ML models, and not spend a lot of time building infrastructure or MLOps. So these were some of our requirements, and with this approach that we talk about, like we were able to build like a GRE-based sequential recommendation personalization model, and we served it to our new members. New members is specifically a difficult problem because you don't have a lot of historical data with new members, right? So it's possible, like you have the famous cold start problem there. So that means like we have to look at the members' first session and try to give them recommendations just based off of that 4 or 5 products they viewed in that session, right? So this is a model we built for that, and we were able to like quickly convert our prototype to a production in like less than 2 weeks of time. And this also, like when we did the A/B testing, it showed that all of our members actually loved their deep learning recommendation, and we were able to increase the click-through rate in our emails like by 25%, which is pretty huge, like for us, like comparing to our previous experiments. So yeah, so then finally, like now our stack actually looks like this, where we have introduced TensorFlow into most of these places. Like I won't go into too much detail here, but we have TensorFlow now. We have the capability to run feature engineering on TensorFlow. We can build models with TensorFlow. Now we can also use real-time inferences using TensorFlow extender library. Can talk a little bit more about that. But let's start with like some nice things about Spark. So this part you can think of, the Spark is going to simplify our big data processing platform, right? So reasons why I really like Spark is like you can write code in any different languages. You can have code in like Java, SQL, Scala, Python, R, anything, whatever fits your requirement, right? You can build pipelines on single nodes and clusters. You can work on structured and unstructured data. You can build batch and streaming pipelines. You have a lot of nice distributed machine learning. Oops, I don't know what I did. You have a lot of nice distributed machine learning libraries, which kind of like helps you speed up a lot of your machine learning and learn quickly. So yeah, so data pipelines in multiple languages. You can have yeah. So yeah, easy to use like APIs in SQL, Python, Java, R, and Scala. And then you can create your own user-defined functions, which kind of expands the existing capabilities in Spark. And you can build your own, you can add your own libraries into like a user-defined function and then use it in any languages. So in an example, you can see, you can think of it as like data engineers will create some functions that they want to use in their ETL pipelines, right? So in this case, like there's a simple function, which is basically saying hello. And then once you create the function as a UDF, you can register it into like the SQL context. Now data analysts or data scientists who doesn't use Python, but solely work on SQL can just go to the SQL UI and or the SQL context, and you can just say hello, and you can use the same UDF in SQL, and that kind of simplifies people to use like stick to the languages they love and not roam around. Let me just quickly. Yeah. So yeah, this is a new thing that came up, I think 2 years back. Pandas UDF is like an advanced version of UDF, but it's it's an awesome thing because people who are more familiar with Pandas data frames and not Spark data frames can now manipulate like Spark data frames in Pandas, right? So basically what that means is instead of creating a UDF that is solely Python based, you can actually get a Pandas data frame or a Pandas series in your UDF and then write like just Pandas code to like tweak or data wrangle your data frame to whatever you need, and then return it as a Pandas series or Pandas data frame, right? So if you are someone who's very happy with tweaking, manipulating data in Pandas, this is something that you should definitely look at. In our specific case, we use Pandas UDFs to do inference. So in our inference pipelines, we load our deep learning models into a Pandas UDF, and then we can just directly plug this inference UDF into our inference pipeline, and then you kind of get recommendations off of deep learning. We'll talk a little bit more about that as we get to it. And then Spark ML, as I said, is built-in ML library in Spark, which provides scalable implementations for many common ML algorithms, which includes traditional models like regression trees, naive Bayes. Also has some fundamental text models like bag of words, word to vector, TF-IDF, and also has like ALS-based collaborative filtering. You can also see some approximate nearest neighbors things like locality-sensitive hashing, random projection. So a few things to like, if your data sets are huge, it kind of helps you to you do approximate stuff. You can also integrate a lot of libraries to Spark itself. You can integrate sklearn, XGBoost, TensorFlow, PyTorch, and a lot of different libraries. So now let's just quickly see how a traditional Spark pipeline would look like. So this is how our Spark pipelines look like for a lot of our projects. It's basically read the data from whatever the data source is, then do a bunch of data pre-processing, feature engineering on Spark. And then we write the data as like Parquet format onto like S3 or some sort of persistent store. And then from there, we read and load that data into our models using Spark. And then we store these models to MLflow or again to S3 or another persistent store. And then we build our inference pipelines, which can be batch or streaming. So this is how things would look in a very solely Spark-based land. It will become more prominent as we go through, like integrate more things to it. So now any questions till now, Denny?
Yes, sorry, I muted myself, I completely forgot. Okay, so one, which I'll answer just because, will this deck or recording be available after the presentation? Absolutely. The presentation actually is already being posted on YouTube as we speak. So I'll go ahead and actually provide the link to both the Zoom link as well as LinkedIn, just in case you want to go ahead and refer to it. That's the first thing. The second thing that we definitely want to go do is ask the question. Here we go. Sorry. There's a great question on LinkedIn. I've actually started answering the question, but I'm sure, Ronnie, you have your own context that you'd like to add as well. So let me go ahead and ask that question. It's related very much to the pandas UDF, by the way, which is very much how to ensure optimal model parallelism that's achieved in distributed deep learning in Spark. Do you recommend any monitoring solutions to identify any of the bottlenecks? Now, to provide some context, what I did is I went ahead and answered the fact that, okay, since Apache Spark 2.4, there's the barrier execution mode with pandas UDFs. This allows that better integration between the two. But during the training phases, you probably still want to go ahead and actually monitor where there's going to be some serialization efforts, because as much as you try to parallelize, there's still going to be some aspects of the model that will force some forms of serialization. So saying that, anything you think that should be added to that?
Yes, this was a support ticket I filed to Databricks. We were actually seeing an impact on pandas UDFs, and like our jobs were failing because it was trying to push a lot of data together into like one node. So one optimization they recommended and which worked is to limit the pi arrow max records per row or something like that. There is a parameter that you can update.
Oh, yeah, right.
So then we set it, I think by default it's like 10,000 or something. So we updated it to like 100 or some value. I don't know, remember right off the top of my head, but that is a nice optimization that we had to do to like make PAS work, because otherwise what it's going to do is it's going to trigger a lot of these tasks, and each of the tasks is also going to load this deep learning model, right? So that's like 300 MB per task. And if your node doesn't have a lot of memory, it's actually loading. If you have like 10 different tasks, it's actually loading like almost 3 GB of data into your memory. So there is an optimization that we have to do over there, but limiting that, I think it was max rows per record or something like that. There is a parameter in PyArrow that we had optimized.
Right. Thanks for the reminder. Yes, because in the end, what you're doing is you're making use of the Python memory allocations. And so basically PyArrow was basically overloading it. And you actually have to specify at that level, because otherwise, in essence, the pandas UDF was basically trying to use up every single resource of that particular Spark worker, as opposed to because the Spark worker itself you couldn't allocate across all of them. You're still focused on that particular one worker, right? Good call out, dude. Yeah. That excellent. So there you go, Ron. Thanks for the awesome advice, Ronnie. That's a really good call out. Okay, I think we can continue on. I actually need to go ahead and move some spam from our from our sessions right now. So I'll go take care of that. You go ahead and continue presenting.
That was a great question, by the way. Like we faced the exact same issue. So we had like a support ticket, and we worked it out with the support person. And yeah, a great question. So cool. So now let's move to TensorFlow and like why TensorFlow and some of the nice cool features of TensorFlow, right? So yeah. So as I said, TensorFlow is a very popular machine learning framework maintained and even used within Google. And I really like this principle of version 2, where they have integrated Keras into the whole TensorFlow package, right? So now they have this core principle of progressive disclosure of complexity. And it's a very nice concept of you shouldn't throw someone off a cliff, and then they should like slowly learn and become more advanced, right? And it has helped me a lot because I was initially more familiar with Keras, but not a lot of the complexities with TensorFlow V1, right? So I really love this approach, because as you work on with the new version, you'll see that there are places you would need to actually go down and create your own custom training loops. But when you don't need to, you don't have to, right? You can just use .fit and then get it done, like get the built-in stuff functionality. So I really like this principle, and it's an amazing, like right now the library is pretty well integrated, so you can choose your complexity or choose your own in like difficulty level when you want to dive into like deep learning. Other than that, TensorFlow also has TFX, which is TensorFlow Extended, which kind of extends TensorFlow's capabilities beyond just model building and to like build end-to-end machine learning pipelines, right? So you can do feature engineering, you can do like model monitoring, model serving, and a bunch of issues, a bunch of things. It also has a cool ecosystem of extension libraries, which kind of expands it beyond traditional deep learning. So you have, we'll talk a little bit more about some of the libraries, but you can do reinforcement learning, you can do like probabilistic models, and a bunch more things, right? And finally, I really love that they have a whole set of tutorials and guides to build any sort of models. So it's pretty cool. Check out these links if you haven't, and you can quickly get into, building some things off of your own. And yeah, most of these notebooks in that link also have a Colab link. So you can actually, interactively play with Colab and, play with building different models and stuff. So I highly recommend using that if you're interested in some of these TensorFlow stuff. Yeah, so TF data is TensorFlow's version of data manipulation and data loading. So it's a TensorFlow API for that. So basically it deals with TensorFlow datasets. So TensorFlow datasets are like optimized for loading data into a model, right? So with TensorFlow datasets, it kind of provides a lot of optimizations behind the scenes, which is like prefetching and caching. So for example, if you're using a GPU cluster for training your model, a lot of the CPU things are just sitting idle, right? Because all the work is happening on CPUs. What prefetch does is while your GPU is training on like everything else, prefetch uses a CPU to prefetch like the next n batches of data so that it's ready for the GPU when it's idle. It's getting done with the current task, right? So it's a very nice optimization, and it's just one of the optimization, but it provides a lot of these nice things, which kind of helps you train a little bit quicker. You can also have, so there are a lot of parameters, but if you don't want to like, sit and tune everything individually, you can just call this thing called auto tune, which is going to automatically adapt prefetching and a lot of your parameters to follow, it kind of monitors, I think, the instance usage and kind of tunes these parameters based while you're training your models, right? Which is also a very cool feature. And then finally, you have something called TF Record dataset, which is basically a TensorFlow dataset, but now you can also load data directly from TF records. We'll talk a little bit about what TF records are, but TF records are the native file format that's used in the TFX platform, and native file format to load data into TensorFlow. So TF Distributor is a new library that part of TensorFlow again. It came, I think it's part of V2, where it provides you like a way to do synchronous and asynchronous distributor training. So they call it training strategies, and you have different strategies for training on GPUs, for training on TPUs, and a few other options. So automatically it assigns like a default strategy to every training loop. So even if you don't specify a strategy, there is a default strategy, which is automatically added to your code, right? Which kind of means that if you have a single node development code, if you currently have a TensorFlow 2 code, you can simply convert it to a distributed code by just adding a few lines initially, like in your code, existing code, right? So, which is pretty cool. Like, so you are like future-proofing your single node code to be like distributed in the future, right? So all you have to do is like something like this. Basically, you just specify when you use a GPU or a TPU, what strategy do you want to use? If not, just use the default strategy, right? And then you just wrap all of your more data loading and your model building stuff into this with my strategy, and that's it. And this is if you are just using pure TensorFlow to do distribution. So this will involve like MLOps. We wouldn't be using this, but this is again pretty cool because you can quickly move from single node to distributed. Again, another caveat is when you're distributing your model building across multiple nodes, you also need to distribute data sets, because if you don't distribute a data set, you are ultimately just building the same model with the same data on every single instance, which kind of beats the purpose of distributed training, right? So previously you had like two different policies to distribute a data set. You can just distribute a data by data, which means like it kind of goes round robin and picks like this row goes to this worker, this row goes to this worker, and it kind of like assigns different rows to different workers. You also have a file policy, which kind of assigns like certain files to certain workers. So there are different strategies we can develop if you're more interested. Again, there are like very nice documentations on all of these things on TensorFlow's website. And then the other piece is like TensorFlow Extended. As I said, this is the end-to-end machine learning platform for TensorFlow. So if you're purely a TensorFlow ecosystem or like place, this is what you would be using. So you have like things like data validation. You can do TensorFlow Transform, which is basically feature engineering. Then you can build your models using TensorFlow. It also has a cool library to do model analysis, which will actually monitor your models even in prediction for drift and a bunch of other things. So it's again a nice library. And then finally you have TensorFlow Serving, which kind of helps you serve your model. So this will be important if you want to do a real-time lookup service where you want to host your model behind like an endpoint, and if you want to serve recommendations in real time, right? So that's the thing you'd be using for that. Yeah, so as I kind of walk through, there are some cool TFX components, which is TensorFlow Transform, which lets you do feature engineering and transform. So this is an alternative to using Spark. So again, if you are a pure TensorFlow platform, this is what you would be using, or you should be using, which kind of simplifies your feature engineering and transformations. TensorFlow model analysis, again, lets you do model validations and also lets you monitor issues in your model, issues in your data, issues in your like drifts, and a bunch of things that are already baked into the TF model analysis library. TF serving, as I said, is which you would be using like if you want to do real-time inference. So this is a core component which is deploying a very high performant REST endpoint, and you can host it behind any sort of Docker service. It kind of loads and serves a model at this endpoint. Docker containers are provided by Google with different flavors of TensorFlow, with different custom build and everything, and you can like pick the one that works best for you. Since this is also Docker based, you can also scale it. You can put it behind a load balancer. You can put it behind like a scalable container service, and have a very highly performant, highly scalable solution for online recommendations, right? And TF Recommenders is a new popular library for an extension library for TensorFlow. So this helps you to build deep learning recommenders. So this is what we used for our recommendations, is the new one we built. Basically, it lets you build ranking models, retrieval models. It has like a nice a few wrappers for the models for custom metrics and losses specifically for recommendation systems. It also exposes Google's scan and approximate nearest neighbor engine, which is again very performant and lets you do approximate nearest neighbor lookups in milliseconds, right? Which is very important when you want to build something real time, because you don't have a lot of time to think and give recommendations. So you need to actually approximate and find the best match as fast as possible. So TensorFlow Recommenders exposes the scanner library as a layer, and then you can use it in your pipeline, in your lookups, and wherever you need. So yeah, as I mentioned, it already has support for building retrieval models, ranking models. You can also build multitask models where you want to optimize on different objective functions. For example, if you want to optimize on clicks and purchases, so you can build those sort of models. It has deep cross networks, which captures explicit feature interactions between two different features. So yeah, check it out. Again, TF Recommenders has great documents, great tutorials if you want to dive deep into it. And I'll just quickly call out some other extension libraries we have explored and we are currently exploring. One is TF Ranking. TF Ranking is again to build ranking models. So you can build learning to rank and a lot of ranking specific models. It includes commonly used functions, loss functions for ranking, commonly used ranking metrics like NDCG and MRR. The other library is TF Agents. So TF Agents helps you build reinforcement learning models, right? So how we have explored this is it also lets you build bandits, so multi-arm bandits. So you can build a bandit algorithm or bandit testing framework using this library. So yeah, so these are some of the extension libraries, but again have very nice documentation and tutorial notebooks that you can explore. Right, and then finally, this is where if you want to use BERT or all of the new NLP stuff comes in. TensorFlow has something called TF Hub, where they kind of store all of pre-trained models, most of the pre-trained models. So if you want to play with image models, it's already there. If you want to play with audio models, it's already there. If you want to play with text models, it's already there, right? So all you have to do is you can just pull any of the pre-trained models as a layer into your deep learning, custom deep learning model. And then all you have to do is basically just specify the path, load it as a layer, and that's it. And then here you can see a lot of the domains that they focus on. So they have text domains, they have image domains and video domains and audio domains. So you can just load these things as a layer to your deep learning model and just use assets, right? Or you can fine tune it. It's completely up to you, but it's already readily available. If you want to move to the latest and greatest cutting edge, technologies and algorithms and models. Yeah. So now let's also revisit that pure Spark pipeline with now what happens if you do a pure TFX pipeline, right? So now if you have a pure TFX, you would be reading the data again. That's the same, but you would be processing using TF pipelines or any TensorFlow specific stuff, and then you would write the data as TF records instead of Parquet or some other formats that's supported by TensorFlow to a store. You would read and then feed these TF records to the model itself using TF data. You then store your model to S3 or some sort of persistent storage, and then finally, you could create inference pipelines, which can be batch or streaming. Any questions till now?
Actually, there have been a lot of great questions. So one from the, let me go back and actually chime in some of the older ones, because there's actually some good ones basically that the people were asking. So for example, one of the things that you had mentioned before was this concept of batch versus online inference. And so there was the person that was asking was could you provide an example of that? And let's definitely talk about from your particular environment. In my case, I went ahead and decided to say, hey, if you're doing a cycling site, right? The batch inference would be something akin to like, okay, you're a new user, you just registered on the site, so we're going to generate some recommendations for you, versus the online inference. This in this case would be more akin to like, oh, okay, hey, you just added these wheels to your to your cart, shopping cart. We typically group it together with these pedals, right? That was the example I used. But I figured maybe since you're the speaker, you've got some better examples than the one that was very specifically cycling related. So.
Yeah, I think batch versus real time is more of a conversation of what you really want. So, for example, for us, like our existing personalization algorithms are run daily, once a day, right? And then what those jobs do is it just creates a list of recommendations for this member ID, or like a certain list of products for each member, right? We don't want these recommendations to be updated like in real time, because running real time also has its associated cost, because you're hosting a lot of things. So in these cases, you can have like maybe a job that runs like once an hour or twice an hour that captures all the latest activities and just builds your model off of that, right? So that is basically batch, where you are pre-computing like the recommendations for a member, like before like this before like the session or whatever, and then you store that data somewhere in DynamoDB or like some sort of SQL or some sort of database where you can just easily pull those recommendations, right? So then think of it as an API that's serving, give me all the recommendations for this member ID, and this API is just going to serve the pre-computed list of stars. So that's the batch, like especially in our context. So yeah. So you can look at all the activities of the member until yesterday and then give them recommendations for today, right? When we say real time, this is like, for example, very similar to Denny's example, but you are looking at a wheel, right? But we can also look at what color was the wheel, what sort of how many spokes it had, or like like the width of the tire and a lot of features like that. And then within that session itself, we can now say, because you looked at these wheels, you might like these colors of these things as well, right? So it's kind of enticing your or increasing your engagement with the site itself. So it kind of helps you, especially in recommendations terms, it helps you reduce like that long tail. So it kind of easily helps you to like find products on the site. So in a fashion context, you can think of it as you're a member who was coming to a site. You might not have a lot of historical data. Think of it as a new member, right? You just joined, you looked at like a black dress, and you looked at like a red dress and a black pant and a few things. Now, based off of those activities, we can say that you might like black dresses, or you might like black color in general. So those are the things where we will be using real time, because you want to make decisions in real time in the same session, and you want to capture this member like as soon as possible, because most of the members who join our site have like they might have like a short lifespan. So we want to like make sure they sick and they get to what they need like as quickly as possible. So that's where you'll be using real time. Does that make sense?
It does, absolutely. So thank you for the context. There is another question, which is, what would be the most important benefit for using the complete TF pipeline, and specifically the TF pipeline that you were just referring to right now?
Right. I think that's again like an organizational preference. Especially, I think another factor that would other thing that would factor in would be, are you on AWS or Google Cloud, right? If you're on Google Cloud, there's also like already built-in support for running stuff on TFX and TF Transform and everything, right? So that is something I think like it's again completely organizational preference. I've seen like blogs where entire companies are like entirely on TFX platform, and it's working perfectly for them. So most of the time, I also seen that they work on Google Cloud. So I think Google Cloud has like natively integrated with a lot of these things that we talk about. But if you're on AWS, it might be. I don't know. I haven't explored that a lot, but I think that's one of the reasons.
No worries. Perfect. Well, we've got a little bit of time left. So why don't we just go right to the MLflow portion of it?
Yeah. So the MLflow portion is pretty simple. MLflow is again an open source platform for managing your ML lifecycle. It lets you track experiments, reproducible, experiment reproducibility, deployment model management, works with most of the common MLflow libraries, seamlessly integrates with Spark and also TensorFlow. So experiment tracking is where you can track every single parameter. You can also track your models. You can track any sort of artifacts. So this can be like plots or like, confusion matrices or all of those things. You can track every single thing associated with the run. And then what that lets you do is you can actually now compare the metrics between different runs and actually choose the best model, best model from your runs. Recently, there's also auto logging capabilities, where you just say mlflow.autolog, and it's going to log everything by default. You don't have to worry about doing mlflow.log params or like log metrics. It's actually just going to track everything automatically. Yeah, and then model management is, again, using MLflow model registry. Again, a pretty cool tool. We have explored a lot of solutions in the past, but this works for us, where you can transition a model between staging, prediction, and an archive stage. So think of this as a single source of truth for all of your models, right? And all of your models are managed here. So you can say your downstream processes can now say, like, give me the latest prediction model for this forecasting thing, or give me the latest prediction model for this thing. So we don't need to worry about like where this model is stored, different versions and everything. All the versioning and everything is managed within the model registry. It's a very cool thing, and we use it for this particular purpose. Finally, in MLflow, there's also a capability to serve models. So once you save your models to MLflow, you can now serve them through a REST endpoint. It's just a single button click, and you can actually, I don't have this updated, but basically it's just a single button, and then you can just say serve this model, and then it's going to automatically generate an endpoint, and then you can now just call that endpoint and get real-time inferences. It works pretty good if your model is pure flavor of TensorFlow. For our specific case, because we use TensorFlow Recommenders, we couldn't use that function. I think there is an open MLflow ticket to address that and provide custom serving images. So hopefully soon that'll be done. I'm just going to rush through this because I realized I'm running short on time. But now we talked about all of these individual solutions. Let's talk about how we can combine all of these together, right? And then get to what I was initially talking about, get to that simple, quick training and all of those things. So TF records, as I said, is a native TensorFlow format. It stores a sequence of binary records, and it's called examples. So each of the records are called examples. So the binary performance specifically in TF data helps improve performance as they take like less space and can be read more efficiently. It is optimized for very well with TFX library. It's very efficient in storing sequential data. So it's like much more performant than saving things in Parquet because of this binary approach. So anyways, this is used natively in TensorFlow. We'll get to why this is important. So now there is a library for Spark, which it's been around for a while, but this lets you save and read your Spark data frames as TF records. So all you have to do is change your format to TF records, and it's actually saved this the data frame as TF records. You can also read the same thing as TF records. The reason why we use TF records is it provides you with that flexibility that I was talking about. Like, for example, if you want to do your feature pipeline or the feature engineering pipeline in TFX or Spark, but later you decide I want to move to TFX. This is just going to give you that modularity, because this thing is just reading TF records and writing TF records, right? So you can think of it as a different modular piece of things where you can switch between these framework as you need in your different ML lifecycle phases. There are other approaches like Petastorm, which kind of achieves a similar thing, which kind of converts a Spark data frame to like the TensorFlow dataset, but you kind of lose this interoperability with TFX. So that's why reading and writing in TF records is pretty important, at least from my perspective, because in the future, if you want to use TF Transform instead of Spark to feature engineering, this kind of sets us up or future proofs us for that for a particular purpose. This is the main thing, the core thing that's pretty awesome. It's part of the TensorFlow ecosystem. Spark TensorFlow Distributor enables running a lot of the synchronous TensorFlow distribution strategies inside a Spark job. So the main thing that this does is it's actually delegating your cluster management and the communication between nodes to Spark. So Spark is now going to handle all of that. You don't need to worry about like setting up anything to set up this whole distribution thing, right? Also lets you run this whole distributor training on CPU cluster if you really want CPU clusters. For us, we compared that, and training something on CPU clusters is like 3x slower than training something on a GPU cluster. But there is an option to do that. It also supports the custom strategy option, where you can specify, if you don't like the default strategy that comes with Spark TensorFlow Distributor, you can specify any other TF distribution strategies. So in this picture, you can also see you have like different Spark nodes or Spark workers. TensorFlow Distributor is just going to sit on top of that and just coordinate everything between these things, and then also lets TensorFlow speak to this nodes as a part of the TensorFlow cluster or distribution strategy. So Spark is like coordinating all of this thing for us. It's very straightforward to use this. We just need to specify the data loading and the model building part in a function, in a helper function called train, or anything that you want to call it. And then also need to specify the number of workers in the cluster. And then all you need to do is call this mirrored strategy runner, and then specify the number of workers in our cluster, and then just call your helper function. That's it. That's all you need to do, like distributed training in Spark for TensorFlow. So yeah, this is the main slide for this whole talk, because this is what brings everything together, because you just literally converted your single node development code or single node TensorFlow code into like a distributed thing right now, just with this one line of code. Right, so this is just a pro tip. How TensorFlow Distribute works is it assigns like certain nodes or one node as a chief node, and all the other nodes as workers, right? So chief node, like it becomes important because think of it as you're saving your model to S3 or some path, right? For every checkpoint or after training. You don't want all of your workers to do the same thing. You don't want all of your workers to save the same thing to S3, right? You just want like one of them to save it to your store. So this is why we need to know which one is the chief node. So you can easily actually just refer to this TF config thing in OS and in your environment. So this TF config is automatically set by this mirrored strategy at the library, right? So you can just use this to determine, is this a chief node or is this a worker node? And based off of that, you can actually save your model differently. So your workers can now save it to like maybe some dummy local location, but your chief can save to a persistent S3 store or something. Finally, another pro tip is, this was something we learned the hard way. You can train your model for days. You can train your model for 10 days, but if you don't explicitly specify how to save the model by using a callback, you don't get back those models, because this is running in this distributed context and it's running in that mirror strategy function. You don't get the finally trained model out of that function. So you have to explicitly save your model. So you have to say, save this model to this path. But if you don't do that, you might be running for training for days, and then there is no way to get your final model. So you just lost all of your work. So it's pretty important when you're using this approach to use like a model callback or backup and restore. You would also do the same thing if you want to save checkpoints, right? You'd use the same approach and you'd save your checkpoint so that you get some fault tolerance. So if your training fails for some reason, if a worker died, you can save some checkpoints and reload the checkpointed model and then restart training from that epoch. So you would still follow the same approach for that particular purpose. Right. So now we've done with training. We have all of these pieces. We saved our final model to MLflow, and then now everything is in MLflow. Everything is like, in the model registry. What you have now is batch inference, right? So batch inference, again, it's a pre-computation Spark job where it's just looking at all of the activities until now, and then just predicting or giving recommendations for the next day or for the next hour or something, right? So that's where batch inferences comes in. So here in batch inference, we use pandas UDFs again. So you load your model from MLflow into this pandas UDF, and then you just call the UDF in your existing pipeline. So if you have this data frame that's called inference data, all you have to do is call your pandas UDF and then pass in all of the columns that needs to be fed to the model as input, right? So you can think of like different columns, like what is the color, what is the brand, what is the name, right? So you can feed all of these as a structure, like data type, and then it kind of feeds everything into the model, and then now you get recommendations right out of it. And then now once you run this, your inference data frame is just going to have like a new column called recommendations, and that's it. And you can tweak it and save it to any store you want and serve the recommendation. If your models are pure TensorFlow, as I said, MLflow is getting there with custom flavors of TensorFlow. But right now, if your models are pure TensorFlow, that is, you don't use TF recommenders or anything custom, you can actually load your models directly you can actually load models from MLflow into a Spark UDF. So, and all you need to do is like call this MLflow pyfunc.spark UDF, and you specify the model URI, and then it's just going to create a Spark UDF for you, and you don't need to create anything by yourself, which is pretty cool because creating the UDF requires some sort of tweaking. So if MLflow can handle that, that's pretty cool. So all you need to do is if you create a predict function using this approach, you can just say predict and then pass in all of this stuff, right? In this case, this batch lookup UDF is something that I have to create, and I have to manage. This is a pandas UDF I created, but in this case, you don't need to create anything by yourself. This is built-in functionality you can leverage. Yeah, so then finally a recap on whatever we talked about. We looked at those two different pipelines, but now let's combine all of that. So now if you look at it, this is how our pipeline looks like right now. So for data ingestion, we still use Spark because Spark also gives you a lot of nice connectors to most of the data sources. So you can connect to like S3 or Kinesis or whatever, right? So you can directly connect to that in Spark. You can do feature engineering in data pipelines or in Spark pipelines. And then all that's changed here, instead of Parquet, we save as TF records. And then in the model building part, we read those TF records, train the model, save the model to MLflow. And then in the model selection in MLflow itself, we have another job that just looks at all the metrics associated with this run, compares the metrics, make sure things look good enough, and then we promote that model to production, right? And then in all the downstream tasks, we can now pull the production model. And then in the batch inference part, as I mentioned, we just load the production model and into a pandas UDF, and then just add the UDF to your Spark pipeline. Yeah, so that's basically everything. So the pros of this approach, as I mostly talk about, is it's great for a smaller team. You can quickly move to production from prototyping. You can choose your framework at any stage of your ML lifecycle. It's scalable with minimal MLOps. You can distribute it, load on Spark GPU or CPU clusters. You can use all of TensorFlow's ecosystem and extension. So we can use any of the things that I talked about from the TensorFlow land, right? You have like centralized storage management and everything using MLflow. And there are some open challenges where distributed training does not handle the fault tolerance gracefully. Like your job is going to fail and you have to restart the job, right? I would expect it to automatically handle worker loss or something like Spark does. So parameter strategy, server strategy is another thing that we could be looking at, which is basically an asynchronous training strategy where you have a node that's going to manage all of your parameters, but there is no library for that yet. So that might be a nice approach in the future. Tuning still requires some effort because you have to find the right amount of nodes. You have to find the batch size and a few things here and there. Sometimes the TensorFlow messages can be pretty cryptic and it's very difficult to debug. APIs between TensorFlow and Keras is pretty much in a state of flux. Sometimes they move the library to a different repo. Sometimes they use the same, they put in the same repo. So it's still like in progress. But that's basically it. And then, yeah, if you want to learn more about this, if you want to learn more about how we can use this approach for an online inference thing using Spark structured streaming and more pro tips and a simple demo on Databricks or something, please join me for my talk at Data and AI Summit on 29th. And that's it. Any questions still?
Ronnie, no, this was amazing. We're right at the top of the hour, so let's pause it right now. If you have more questions, definitely join us also on the two things. Actually, I want you to flip back to the previous slide, so that way people will remind people to come to the Data and AI Summit. So you can definitely join us there, where Ronnie will dive deeper into it as well. You can always join us in the MLflow Slack. We actually are pretty active there and answer lots of questions. So that's it for today. Thank you very much, Ronnie. Really appreciate your time. This was a great session. Lots of great questions. I'm sorry that we didn't answer all of them, but again, thanks very much. And we hope to see you actually at Data and AI Summit. It'll be a blast.
Yeah.
So
thanks
very much.
And thanks. All right.
Bye.